understand the next important point, the Hooke's law. Now, many of you must have gone through 12th standard physics. There we must have come across the Hooke's law. So what is Hooke's law? So Hooke's law, the basic statement states that within elastic limit, right? What is happening?
Stress is equal to strain.
Stress is directly proportional to strain.
Yeah, within elastic limit, the stress is proportional to strain. So the stress induced in the material is going to be proportional to the strain. Now, what do you mean by this elastic limit? This is very, very important. This is the question mark. What is the elastic limit? Now, whenever we talk about this proportionality, so proportionality means it is directly proportional to strain. Now, if I remove this proportionality, there will be some constant. So the stress upon strain, if I write, so it will be some constant of elasticity.
Yes,
right? It will be some constant of elasticity, and that constant, okay, that constant we need to take care of it. Okay, what is that constant? We will be studying that in detail. What is that constant? That constant is also known as modulus of elasticity. It is known as modulus of.
Here you have written stress upon stress.
Yes, I didn't get
You
you.
have written stress upon stress.
Okay, wait a minute. Good, thank you. Stress upon strain. Yeah, so that is modulus of elasticity. Now, as you can see, stress upon strain, this modulus of elasticity will also have the same unit as that of stress, because the strain has no unit, so there will be same unit as that of stress. Okay, so within elastic limit, matlab, this Hooke's law says that the proportionality is only up to the particular limited value. After this, the stress and strain are not going to be proportional to each other. Means what? For example, if I take a metal wire and if I try to elongate it, okay, तो एक metal wire लिया, उसको elongate किया, so the amount of force I apply is proportional to the amount of deformation I get. Okay, so this proportionality will be only up to a certain limit. It's not that way that I can apply an infinite amount of load to the wire and it will elongate infinitely. This is not going to happen in real practice. That is why this Hooke's law gives you the limitation to this proportionality. Okay, so the limitation is nothing but it is going to be proportional up to a certain limit, and that limit we also call it as proportionality limit. After that, the materials are either going to break or they're going to behave right differently. Now, what is that behavior of material when we continuously apply load? So that is we need to understand in the next section, which is stress strain curve for the materials. Now here I have divided these materials into two different types, that is a ductile material and the brittle material. All of you know what is a ductile material and what is a brittle material, right? I hope everybody knows that what is ductile and what is brittle. So,
Yes, sir.
Yes.
so we'll just go to the first stress strain curve for the ductile material. Now you can see what is stress. So stress हम लोग कैसे calculate करेंगे? तो stress is sigma, which is load upon area, and what is strain? So it is E, that is elongation upon original length. Let us assume that I have a wire, एक simple wire है मेरे पास, and that wire I am using it. Let's say I have a certain wire which is hanged from a particular fixed support and I am applying the load. Now this is the varying load. I am going to increase this load slowly. Okay, so I am going to increase the load. Load was initially 0. Gradually usko मैं increase करते जाऊंगा by in certain steps. So what is going to happen to this particular wire? What are the stress versus strain values are going to come? That is the graph which is shared next to you, next to this. As you can see, the graph will start from 0 point where the load was 0 and the deformation is also 0, and then we apply load. So when we apply load, there is some fixed cross section of this particular wire. So cross section I already know. So when I increase the load, the stress is going to increase, and because of elongation, more and more elongation is going to happen. Therefore, the strain value is also increasing. So you can see initially the wire increases and we get a inclined straight line. You can see the straight line from point O to point A. Okay, all of you can mark this straight line. And ये straight line क्या represent करता है? So this straight line represents the linear elastic region. What do you mean by linear elastic region? The linear elastic region states that the ductile materials initially show linear relation. That means, for example, roughly, if I say, if I add 10 kg of load, the elongation can be 1 mm. If I add 20 kg of load, kg means into ये करेंगे तो Newton में आएगा. So if I add 20 kg to the wire, the elongation can be 2 mm. If I add 30 kg, elongation is 3 mm. That means you can see the change is constant. The change is constant. The slope is fixed. So therefore, we get a straight line, and inclined straight line has a fixed slope. So it will be happening up to a point A. Okay, that is the first region which we call linear elastic region. What do you mean by elastic is, if I decrease the load, means if I from 30 kg of load, if I come back to 20 kg of load, the wire is going to compress. The elongation now present will be only 2 mm. मतलब पहले अगर 3 mm था, अभी elongation 2 mm बचेगा. That means the wire is completely regaining the shape and the size. वो complete regain करेगा. The wire will not show any permanent traces of the loading in that. Okay, that is up to A point. That is the proportionality limit or the linear elastic limit. Okay, after that point we have certain point called as B. This point A.
Can you explain once again?
Yes, okay. So what I'm trying to say is, I am understanding the behavior of a wire. Basically a simple ductile material I have taken. Let's say you can take steel or a copper, anything. So that ductile material, I am trying to analyze it by applying the gradual load on it. So when I'm applying the gradual load on this particular wire, what is happening to stress and what is happening to strain? What are the different points, significant points I'm getting in that behavior? How the behavior changes after certain regions, that I'm going to understand. So that is why very first thing, when the no load was acting, there was no deformation, I started with point O. Okay, but when I start applying the load, so initially what will happen, when I apply, let's say 10 kg of load, I found that the elongation was, let's say 1 mm. When I add another 10 kg additional load, that becomes total 20 kg of load. Now the elongation is 2 mm. Now if I add another 10 kg of load, now the elongation is 3 mm. That means the elongation and the load applied load, that means the stress and the strain are exactly linear to each other. Are going linear to each other. That's why the slope of the curve is constant, and that is why we're getting straight line up to point A. This will happen up to a particular region. ठीक है, मतलब ये ऐसे कुछ देर तक चलेगा कि up to, let's say up to 100 kg मैंने ये ऑब्जर्व किया कि for every 1 kg of load यहाँ पे 1 mm elongation आ रहा था. I am once again saying 100, 10, 1, all these are significant values. They are nothing to do with the material. Material में क्या values आएगा, they are totally different. I'm just taking these random values to make you understand what is exactly happening. Okay, so I'm not claiming that 10 kg load पे 1 mm elongation आएगा steel rod में या upper rod में. That is not true. It is totally depending on some other parameters which we'll be studying in practicals also. Okay, so don't stick to the values, stick to the concept what I'm trying to deliver here. Okay, so up to A, it is what is happening up to point A, it is complete linear process. It is going. Now after that you will find that कि अभी पहले क्या हो रहा था, every 10 kg पे 1 mm बढ़ रहा था. अभी क्या होगा, you add 10 kg, instead of 1 mm increase, you will find 1.2 mm, 1.3 mm, 1 point something extra mm. That means now the wire is extending more as compared to the load applied. Means the curve will, the line will not be, the relation between them is not linear now. It will be the curved one. That means it will, what do you say? The slope will decrease, the random slope will be coming, and the curve will lower towards strain side. The strain will be more as compared to strain, and this is slightly from A to B. It is shown. Most of the materials will not show significant difference between A and B. जब हम लोग practically ये perform करेंगे, maybe virtually in this particular period, and when the college resumes, we'll be doing it practically on universal testing machines. So there you will understand कि ये A and B points are not significantly different. मतलब बहुत ही precisely करेंगे हम लोग with electronic extensometers of these wires and all those things. Then only we will be able to look at A and B points. Or most of the materials will not show A and B significant difference between A and B points. Okay, but still there will be some 2 points. Up to point B also we call it as the non-linear elastic region. What do you mean by non-linear elastic region? Ki up to point B the wire is elastic, मीन्स अभी तुमने इसके बाद भी पूरा लोड निकाल दिया तो वायर पूरा रिगेन करेगा एंड विदाउट लीविंग एनी ट्रेसेस. अर्लियर लेंथ ऑफ वायर अगर वो जो एल अमाउंट है, लेट्स से इट इज एक्स, then after deforming it and again removing the entire load, it will come back to same original position. That means it is up to elastic region, right? After the elastic region, after that elastic limit, if you go beyond that elastic limit, after that wire turns into plastic zone. Wire turns into plastic region, or we also call it as strain hardening region, where the wire will elongate up to a certain limit but cannot be regained 100%. Complete regain is not possible. Okay, understanding it? So once you overcome the elastic limit, उसका वायर का कंप्लीट रिगेन करना पॉसिबल नहीं होता. इफ यू अनलोड इट कंप्लीटली, तुमने पूरा का पूरा डिफॉर्मेशन फोर्स निकाल दिया, फिर भी वायर में कुछ ना कुछ परमानेंट डिफॉर्मेशन रहेगा. ठीक है, मतलब वो ट्रेसेस रहेंगे. दैट इज द वे वी कॉल इट एज स्ट्रेन hardening region, because the grains in the material, they become hardened, and they, after a certain particular point, they will not come closer to each other as earlier they were having the intermolecular interaction. जो पहले थे वैसे restore नहीं हो पाएंगे, and there will be some permanent set in the permanent set of deformation in the material. Understanding it? So that we observe after point B. Now after point B, you can see there is a surge in this, and then ऐसा कुछ तो ग्राफ आ रहा है. ठीक है, ठीक है. नाउ दिस इज बेसिकली, इसको ही थोड़ा सा एनलार्ज करके यहाँ पे दिया है, मतलब दिस इज क्वाइट हायर ऑन साइड. अभी यहाँ पे ये पूरा का पूरा डिटेल नहीं समझा तो भी टच चलेगा, बट स्टिल विल ट्राई टू अंडरस्टैंड व्हाट इज दिस दिस पॉइंट. आई कैन सी पॉइंट सी, सी डैश सी, एंड दिस पॉइंट डी. ये सी, सी डैश एंड डी पॉइंट्स को वी कॉल दिस पर्टिकुलर रीजन एज द यील्ड प्लेटू, or it is called as yield region. Now what is yielding? Now yielding is basically called as the flow of material. Now you can see ये yield point पे यहाँ पे straight line मिल रहा है हमें, right? For example यहाँ पे straight line मिल रहा है. Straight line का meaning क्या है कि let's say ये straight line है ना, मतलब यहाँ पे अगर मैंने curve पे tangent बनाया तो what I am getting different values of strains for the same value of stress. मतलब क्या है, मैंने force नहीं बढ़ाया, but material क्या हो रहा है, अपने आप ऐसे नीचे गिर रहा है. नीचे गिरा मतलब फॉर एग्जांपल इफ यू हैव सीन प्लास्टिक को बर्न करते हो, तुमने देखा रहेगा, तो बर्न करते हो तो ऐसे पिघल के नीचे गिरता है. या फिर यू मस्ट हैव सीन हनी अगर तुमने देखा रहेगा तो जब हम लोग गिराते हैं तो वो ऐसे फ्लो करके गिरता है, राइट? मतलब उसका थिकनेस कम कम होता जाएगा. तो दैट इज नॉट कंप्लीटली विजिबल इन मटेरियल्स. मटेरियल इतना ज्यादा वेरिएशन क्रॉस सेक्शन का नहीं दिखाता है, बट इफ यू ऑब्जर्व इट क्लियरली ग्राफिकली, हमें क्या पता चलता है कि आई हैव मल्टीपल स्ट्रेन्स. यू कैन सी ये स्ट्रेन का वैल्यू अलग होगा, यहाँ पे स्ट्रेन का वैल्यू 2-3 यहाँ पे बढ़ रहा है, बट द स्ट्रेस वैल्यू इज ऑलमोस्ट कांस्टेंट. So I am not applying any external load, any additional load, but the material is giving you more elongation, continuous elongation. So that region we call it is the yield region. That means material is flowing, plastic flow of the material is seen, and that is for a very short interval of time, and that particular region we call yield point. So here, after yield point, we assume that the material is now entered into the strain hardening region. Up to yield point, practically we can go only up to yield point for deforming the materials, because after yield point they are after yield point, if you deform them, so there will be maximum permanent deformation in the material, and they will never regain their shape and size. मतलब पूरा रिगेन नहीं करेंगे. ऑफ कोर्स द इलास्टिक रीजन में जितना डिफॉर्मेशन था वो रिगेन करेंगे. फॉर एग्जांपल लेट्स से अप टू यील्ड पॉइंट इज अचीव्ड आफ्टर 5 mm ऑफ डिफॉर्मेशन, एंड देन उसके बाद तुमने और लोड लगा के डिफॉर्मेशन तुमने 7 mm तक लेके गए. तो जब तुमने पूरा लोड निकाल दिया है तो 5 mm जो इलास्टिक रीजन में डिफॉर्मेशन था वो रिगेन होगा, बट वो जो एक्स्ट्रा 2 mm तुमने डिफॉर्मेशन क्रिएट किया था after loading beyond the yield point will be permanently there in the material. वो 2 mm कभी regain नहीं कर पाएगा. So that is the importance of that yield point. So in practical applications, we never go beyond yield point. If you go beyond yield point, it will permanently be there, and it will show that the wire is not it is elongated beyond its limit, and further it may break. Okay. So now after that, after this points, so there is a little variation in that. So after that yield points, ये upper yield point है. Yes. एक काम करते हैं, co-host Om, just mute on all of them.
Yes, sir.
Okay. Now let's see. Okay. Now let us go ahead with the same thing. So upper yield point मतलब we get a particular yield point, उसके बाद basically stress value drop होता है, इसलिए we have two significant yield points. ठीक है, but practically इसको अगर हम लोग बहुत ही precise वाले machine पे करेंगे, then only we get these 2 points. Otherwise a normal UTM if you use, and if you use a manual method to record all these deformations, then you will get on a single yield point where you will get a plain line or a curve. यहाँ पे देखो ये plain line मिला हमें, जहाँ पे ये क्या हो रहा था, डिफॉर्मेशन डिफॉर्मेशन वाज इंक्रीजिंग एंड द लोड अप्लाइड वाज कांस्टेंट. ओके, सो दैट इज वी कॉल yield point. आफ्टर yield point if you deform the material, ठीक है, तो क्या होगा, यहाँ पे you can see the stress value increases. Now this stress value increases because of increase in the additional load as well as decrease in the cross section of the material. तो अगर मैंने ये वायर ऐसा था, ठीक है, तो अभी वायर क्या होगा, एक पर्टिकुलर रीजन जहाँ पे भी इंटरनल वीक होगा वायर, उधर वो वायर अभी क्रॉस सेक्शन रिड्यूस करना चालू करेगा, उसका क्रॉस सेक्शन ऐसे कम कम होना चालू करेगा. दिस वी कॉल नेकिंग, दिस वी कॉल नेकिंग, राइट. नेकिंग होगा. नेकिंग मतलब क्या कि क्रॉस सेक्शन जो यूनिफॉर्म था अभी वो क्या हो जाएगा, कम हो जाएगा, क्रॉस सेक्शन विल स्टार्ट रिड्यूसिंग, एंड नाउ वी कैन सिग्निफिकेंटली सी दिस नेकिंग पॉइंट, एंड नाउ वी आर डैम श्योर दैट कि अगर इसके बाद हमने लोड बढ़ाया तो इट इज गोइंग टू ब्रेक एट दिस पर्टिकुलर पोजीशन. अब ये नेकिंग पॉइंट हमेशा सेंटर में आता है ऐसा कुछ नहीं है. It can be towards the one of the end or other end, or it can be anywhere wherever the internal fractures can be there. अभी रॉड मुझे ऊपर से स्मूथ दिख रहा है, but there can be internal fractures, intermolecular spaces, gaps हो सकते हैं. जब ये रॉड मैंने मैन्युफैक्चर या फोर्ज किया था या फिर उसको बनाया था, तो ये रॉड के अंदर मटेरियल मैन्युफैक्चरिंग डिफेक्ट्स हो सकते हैं. तो ये मैन्युफैक्चरिंग डिफेक्ट्स की वजह से ये फेल हो सकता है. ओके, एट सम ऑफ द वीकर रीजन अगर कोई मैन्युफैक्चरिंग डिफेक्ट्स या वाइड्स नहीं है या तो इट विल break at weaker section, जहाँ पे भी weak section है, it will break there. Okay, so now this elastic region से हम लोग ऊपर आ चुके हैं. Now we are in the strain hardening region. Strain hardening region में क्या होता है, it is also called as plastic region, plastic zone also. That means पूरा का पूरा डिफॉर्मेशन अभी रिगेन नहीं होने वाला. तुम जितना भी डिफॉर्मेशन करोगे वो परमानेंटली रहेगा अभी यहाँ पे वायर में, इवन इफ यू अनलोड इट. ठीक है, वो कुछ ना कुछ परमानेंट ट्रेसेस छोड़ के जाएगा, पूरा पूरा परमानेंट नहीं रहेगा, बट ऑफकोर्स some part of it will be permanently there in the wire. Okay, so wire will not completely regaining the shape and size. So now after that we'll reach a particular point known as ultimate stress point, where the necking will be on the verge of breaking, we can call it as. वो बहुत ही वीक, मतलब ये जो वायर है उसका ऐसा शेप हो जाएगा, क्रॉस सेक्शन बहुत कम हो जाएगा. ठीक है, लेट्स से थोड़ा सा डायग्राम खराब आया, लेट्स से आई विल ड्रॉ इट अगेन. ये जो नेकिंग मैंने बनाया था, ठीक है, वो नेकिंग को क्या हो जाएगा, sorry, so this necking will happen like this, ये और weak हो जाएगा, and now we can significantly by normal eye, naked eyes we can see that कि वायर में क्रॉस सेक्शन कम हो रहा है, एंड अभी यहाँ पे ब्रेक होगा. तो दैट इज द अल्टीमेट पॉइंट विच वी गेट द मैक्सिमम स्ट्रेस. देखो ये पूरे ग्राफ में ये सबसे मैक्सिमम पॉइंट है, ये स्ट्रेस का जो वैल्यू है वो सबसे मैक्सिमम पॉइंट है. तो दैट इज द अल्टीमेट स्ट्रेस पॉइंट. वायर इसके बाद जाना मतलब इसके आगे तुम डिफॉर्म करोगे तो यू आर नेवर श्योर दैट कि वेयर इट विल ब्रेक. मतलब ऑफ कोर्स वेयर इट विल ब्रेक तो पता है, बट कितने अमाउंट ऑफ स्ट्रेस पे ब्रेक होगा दैट विल डोंट नो. ठीक है, तो इसके बाद वाला ग्राफ जो है सेम स्पेसिमेन के लिए, मतलब सेम काइंड ऑफ स्पेसिमेन के लिए बार बार करोगे तो इसके बाद वाला ग्राफ रिपीट नहीं होगा. इसके बाद वाला ग्राफ कभी भी चेंज हो सकता है डिपेंडिंग अपॉन दी इंटरनल फ्रैक्चर्स ऑफ द मटेरियल, बिकॉज हर मटेरियल्स आइडेंटिकल एग्जैक्टली नहीं होते, उनके अंदर कुछ ना कुछ मैन्युफैक्चरिंग डिफेक्ट्स हो सकते हैं. ओके, so therefore this graph cannot be similar after that. Failure points may after any time after the ultimate stress point. Okay, I hope I have made you clear कि what is the different stages before breaking. तो जो ductile material है before breaking it shows different region. The very first region is the linear elastic region in which completely linearity was there. Then non-linear elastic region, that is the we call it as this one, we call it as linear. Linear matlab complete proportionality is there. Non-linear matlab now the strain is increasing rapidly as compared to stress. After that we'll get a yield point where without increase in the this stress value, the strain will increase, then we'll reach a necking point, and then we'll reach a ultimate stress point. Okay, and after that it is going to break. So I hope I've made this point very clear. This is you should know for the behavior of stress and strain ductile material. Okay. Now let's go further. Stress and strain curve for brittle materials. Now, as you know, the ductile materials, they have a property that such that they can drawn into wires. So therefore, before breaking, they show this all those regions. But if you go to the brittle materials, ये brittle materials उतना patience उनकी में नहीं होता, वो इतना patience हमें नहीं दिखाएंगे, वो immediately break होते हैं. But the value of stress they can suspend can be different based on the material which you are using. Okay. So in brittle materials, you can see there are only 3 to 4 points. The point 1 is the starting point, that is the origin, जहाँ पे no load was there. Then we have a proportionality point 2. Up to this, the line was completely proportional. ठीक है. Then we have a yield strength. हाँ, अभी ये yield strength ऐसा कुछ होता नहीं है. The brittle material, they are never subjected to yield strength. ठीक है. कि ऐसा कुछ भी नहीं होता yield strength. Why? Because yielding, ये जो brittle materials होते हैं, they cannot be drawn into wires, so उसमें necking and everything is never seen. ठीक है. They will immediately drastically break होंगे. As you can see, if I go to the back side, ये वाला जो slide था, इसमें ये जो break होंगे, after breaking अगर मैं 2 wire के pieces लिए, तो wire के pieces मेरे को ऐसे मिलेंगे. एक wire में ऐसा होगा, cup formation होगा, और एक में ऐसा ये मिलेगा मुझे. After breaking, I will get this. So this is a cup, and this will be a cone. आफ्टर ब्रेकिंग जो दो ब्रेक होने के बाद जो पीसेस मिले उसमें कप एंड कोन अरेंजमेंट होगा, नेकिंग दिखेगा मुझे, बट दिस इज नेवर सीन इन केस ऑफ ब्रिटल मटेरियल्स. ब्रिटल मटेरियल्स विल फ्रैक्चर एब्रप्टली, वो एब्रप्टली ऐसे फ्रैक्चर होगा, एक मटेरियल ऐसा और दूसरा. इट कैन बी ऑन इंक्लाइन प्लेन आल्सो, ऐसा भी फ्रैक्चर हो सकता है. दे विल फ्रैक्चर abruptly. Okay, so they will never show neck formation, and as neck formation is not there, yielding भी हमें नहीं दिखेगा. But most of the times हम लोग yield point लेते हैं calculation में. How we get to that yield point, that will come back to in the proof stress. So after that we'll have ultimate stress point and then fracture point. So brittle material we cannot say कि वो जल्दी fracture होता है, but उसमें इतना सारा stages नहीं दिखता है. Before breaking, it will never show you the visual indication. Like in tensile in ductile materials में हमें visual indication दिखता है, neck formation दिखेगा, and then only we can sure that कि ये टूटने वाला है. But brittle materials will never show any indication. वो stress value बढ़ते जाएगा, after particular point वो ultimate stress पे होगा, and after that immediately it will break anywhere on the section. We cannot even figure out कि कहाँ पे वो break होने वाला है. Okay, that is the case with brittle materials. Okay, so now let us go for what is this dotted line here. That is nothing but proof stress. So most of the materials as well as brittle materials, they do not show the yield point. Yield point नहीं दिखाते. अब ये yield point हमारे लिए important क्यों है? Because whenever we use these materials in design, we design based on their yield strength, not the ultimate strength. For the brittle materials, this yield strength and the tensile maximum tensile strength are moreover similar. बहुत ज़्यादा difference नहीं होता. So in brittle materials we may go up to ultimate tensile strength, but in some of the ductile materials the yield point हमें दिखता ही नहीं है. मतलब ग्राफ मैंने ड्रॉ किया, ग्राफ मैंने UTM पे ड्रॉ किया, बट वो UTM पे हमें कभी भी ये नहीं दिखाएगा, मतलब yield point दिखाएगा ही नहीं. तो अभी yield point दिखाई नहीं, तो how will I come to know कि what was my yield stress, where up to what limit practically I can stress my material when it is used in real practice. That is unknown to me. That is why there is some other method to theoretically find out what is my yield strength. So what is that method? So the method is you locate the 0.2% strain value. मतलब दो stress strain curve तुमने बनाया और वो stress strain curve as you can see यहाँ पे भी yielding नहीं दिख रहा है, इधर भी yielding नहीं दिख रहा है. Yield point क्या होता है कि जो straight आने के बाद हमें कुछ ऐसे surface देगा, right? ऐसा planar surface देगा जहाँ पे मेरा जो tangent अगर मैं बनाता हूँ तो it should be parallel to my strain axis, right ना? This is my yield region, ये मेरा yield region है. But ऐसा रीजन मुझे मिलता ही नहीं है most of the materials like aluminium और mostly aluminium alloys में हमें ऐसा कोई ऐसा yield point मिलता ही नहीं है, copper alloys. So in that case what we do to locate the yield point, we take 0.2% strain. So there is a practical method which is described to us in testing, but as per the ASTM standards, that is American Society of Material Testing. सो टेस्टिंग मेथड्स, तो टेस्टिंग मेथड्स के हिसाब से 0.2% स्ट्रेस स्ट्रेन मतलब मटेरियल का जो तुम्हारा लेंथ है और जो लेंथ तुम्हें ऑलरेडी पता है वो लेंथ के बेसिस पे यू कैलकुलेट द स्ट्रेन वैल्यू एज 0.2%, ठीक है। मैक्सिमम स्ट्रेन तुमने जो भी अचीव किया उसका 0.2% स्ट्रेन कैलकुलेट करो, वो तुम स्ट्रेन एक्सिस पे लोकेट करो एंड देन प्लॉट अ डॉटेड लाइन पैरेलल टू योर प्रोपोर्शनैलिटी लिमिट। जो तुम्हारा प्रोपोर्शनैलिटी लिमिट का जो वैल्यू था उसको तुम पैरेलली लाइन बनाओ, ये लाइन कहीं पे जाके कर्व पे इंटरसेक्ट करेगा पॉइंट बी पे एंड दैट वैल्यू आई विल बी यूजिंग एज माय यील्ड वैल्यू। Okay, that value I'll be using is my yield value. Means practically I can use that is the maximum capacity of my material. अगर वो value से आगे जाएगा तो it will show you the permanent deformation which are visibly seen. 0.2% strain is very less, so it most of the times it cannot be seen. It doesn't cause much changes in the dimension. 0.2% is very less actually. So that is why we have taken this 0.2 as per the standard offered by these testing methods. Okay, so and that is also called as proof stress. So it is the proof stress means what? It is a stress, it is a proof for that कि इसके बाद अगर तुम जाओगे तो तुम permanently deform करोगे मटेरियल को, इसके पहले अगर रहोगे तो you are well in the elastic limit, elastic region where you can deform the material, you can regain the shape and size. That is why it is called a proof stress. Okay, it is the theoretical value which you have assumed for practical use. So I hope I have understood, you have understood this particular part. That is stress strain curve for brittle materials and stress strain curve for ductile materials, and what is the proof stress value, why it is required. Okay, so you should know what is the proof stress and you should know why required. So why question will be there to you whenever you go to any vivas or something or any design concept. Yes, Sania is raising some hand, you can ask. Yes, Sanya, is there any question or by mistake you've done? Okay, fine. So let's go to the next part, the behavior of material. Now, whenever we test these different materials on UTM, that is universal testing machine, for getting the stress strain curve, मतलब उस सब मटेरियल स्ट्रेस स्ट्रेन कर्व लेने के लिए क्या करना पड़ता है? तो हमें ऐसा नहीं है कि मटेरियल का एक पर्टिकुलर स्पेसिमेन साइज होता है. फॉर एग्जांपल नॉर्मल टेंसाइल टेस्ट, the material size is you should take a rod of 10 mm cross section and 250 mm, that is 25 centimeter in length. मतलब तुम्हें एक ऐसा रॉड लेना है जिसका क्रॉस सेक्शन होगा 10 mm and 250 mm is the length of that particular specimen, and वो रॉड को हम लोग यूनिवर्सल टेस्टिंग मशीन में ये करते हैं. We will be discussing quite more on whenever we'll go to practical session जहाँ पे हम लोग इसका और डिस्कशन करेंगे. तो उसमें हम लोग उसको टेस्ट करते हैं एंड देन टेस्टिंग के बाद हमें स्ट्रेस स्ट्रेन कर्व मिलता है. तो ये मोस्ट ऑफ जो स्ट्रेस स्ट्रेन कर्व्स है वो कर्व्स के हिसाब से भी क्लासिफाई दीज मटेरियल्स. मटेरियल इलास्टिक तो है बट उनको क्लासिफिकेशन हम लोग करते हैं. सो यू कैन सी द क्लासिफिकेशन आई हैव मेड टू यू. सो यू कैन सी द वेरी फर्स्ट वन इज लीनियर इलास्टिक. मतलब हमें क्या मिलेगा कि मटेरियल स्ट्रेट लाइन में परफॉर्म कर रहा है, सो देन वी कॉल इट एज लीनियरली इलास्टिक मटेरियल वेयर वी हैव अ लीनियर रिलेशन बिटवीन स्ट्रेस वर्सेस स्ट्रेन. ठीक है, यू कैन सी द लीनियर here, stress versus strain is linear, that is why slope is constant. मतलब यहाँ पे जो मॉडुलस ऑफ इलास्टिसिटी होगा वो एक ही सिंगल वैल्यू होगा. ओके, देन वी हैव अ नॉन लीनियर इलास्टिक मटेरियल्स. मतलब ऐसे मटेरियल्स हैं जिसमें शुरुआत से ही क्या होगा, स्ट्रेस एंड स्ट्रेन विल नॉट बी exactly proportional to each other. The best example here is the composite materials. They do not have exact straight strain curve. मतलब whenever we have mixing of materials, they will not show me the same linear relation as that of pure materials. They will always show some non-linear characteristics. So these are called as non-linear characteristics. Most of the alloys, most of the composite materials, they tend to give you the non-linear elastic properties. Then we have elastoplastic or viscoplastic. So these properties are like up to certain limit they are completely elastic, but after that suddenly they will drop. For example, ये नॉर्मल क्लेज जो आते हैं, विस्कोप्लास्टिक क्लेज और द पॉलीमर मटेरियल्स, दे शो दिस काइंड ऑफ कैरेक्टरिस्टिक्स, जहाँ पे इनिशियली तुम पॉलीमर को इलोंगेट करोगे तो इलोंगेट होंगे, बट सर्टेन लिमिट के बाद स्ट्रेस इज जीरो, स्ट्रेन रैपिडली बढ़ेगा एंड इट विल ब्रेक. सो दैट इज द थर्ड केस. देन परफेक्टली प्लास्टिक. परफेक्टली प्लास्टिक मतलब ऐसा है कि जहाँ पे स्ट्रेस अप्लाई नहीं किया, इमीडिएटली डिफॉर्मेशन हो ही नहीं रहा है, टूट रहा है डायरेक्टली. द बेस्ट एग्जांपल इज योर ग्लास विंडो. ज्यादा कोई इलोंगेशन दिखता ही नहीं हमें, तुम अपना स्ट्रेस अप्लाई करो टूटेगा. तो स्ट्रेन इज इनफिनिट, मतलब वो कब तक बढ़ेगा हमको पता नहीं है. Okay, so that is the perfectly plastic region. Then we have elastoplastic with strain hardening. Now in some of the alloys we see that कि initially उनका grain structure हम लोग अगर deform कर दिया है तो grain structures के deform you will be again studying in this in detail in your MSM subject, that is material science, where you will understand कि हम लोग elastic properties material का कैसे change कर सकते हैं, what are the different properties. You must have heard of hardening of the this one vulcanizing of rubber and hardening, nitriding, then addition of sulfur to the steel, addition of chromium to the steel, what these additions, what difference they make to the elastic properties of that pure material. So you are going to learn very in detail in MSM, that is material science. That is not a scope of the strength of materials. That is why I'm just displaying you the graphs. Okay, so elastoplastic region is you can change the behavior by adding some different foreign materials or the impurities. They are not impurities basically, other than iron or steel. Iron, मगर iron में मैंने और कोई material add कर दिया, just like carbon अगर मैंने add कर दिया तो it becomes steel. तो steel का characteristic अलग है, iron का अलग है. अगर iron में carbon के साथ मैंने chromium add किया, क्रोमियम ऐड किया, कैडमियम ऐड किया, या फिर कोई अदर मैं इम्प्योरिटीज ऐड करता हूँ तो उसका प्रॉपर्टीज चेंज होते जाएगा. सो दोज हार्डनिंग प्रॉपर्टीज वी कैन स्टडी इन मटेरियल साइंस. ठीक है. सो द अदर वन इज आइडियल रिजिड. दिस इज हाइपोथेटिकल केस. आइडियल रिजिड मतलब रिजिड बॉडी जो कितना भी स्ट्रेस अप्लाई करो स्ट्रेन होगा ही नहीं, मतलब डिफॉर्म होगा ही नहीं. दैट इज कंप्लीटली हाइपोथेटिकल. वी डू नॉट हैव एनी रिजिड बॉडी इन प्रैक्टिस. देन आइडियल फ्लूइड. आइडियल फ्लूइड इज ऑल्सो हाइपोथेटिकल बिकॉज आइडियल फ्लूइड ऐसा फ्लूइड है जहाँ पे तुम जरा भी स्ट्रेस नहीं अप्लाई करोगे तो भी डिफॉर्मेशन होगा. सो दैट इज आल्सो, these are two extreme ends. All these material they lie between these two regions, ideal region and ideal fluid. Okay, so I hope you have understood the types of material behavior and what are the different types based on their elastic behavior, which you get out of the after drawing the stress and curve, after testing these materials on the UTM, that is universal testing machine. Okay, so let's now go to the next part of the topic, the moduli of elasticity. So in Hooke's law, we studied something about modulus of elasticity. Moduli is a ruler for elasticity. There are three different modulus of elasticity, which are not new to you. You have been using this in earlier 12th standard, but let's discuss them. So modulus of elasticity, the very first modulus, as we have, what is modulus of elasticity? Basically, it is the stress upon strain. It is stress upon strain, right now. So as we have three different types of stresses, we'll have different types of strains, and we'll have three different modulus. So the very first one is the Young's modulus. Young's modulus. Okay, it is denoted by either Y or the most commonly used is E, capital E, capital Y or capital E. Okay, now what is Young's modulus? So Young's modulus is nothing but it is longitudinal stress upon longitudinal strain. Okay, longitudinal stress upon longitudinal strain. That is your Young's modulus. Longitudinal, yes, Aman Gautam. Longitudinal
yes,
stress
sir.
upon, yes, you asked.
यस सर. यंग्स मॉड्यूलस में आपने वो गामा होता है ना, मतलब साइन, मतलब
क्या
साइन जो होता है उसका आपने वाई बोला, मतलब
हाँ. No, there's never gamma. None of the book will give you gamma. Either Y or E.
okay,
Gamma
sir.
is some different thing. We'll be studying that later. Okay. We never use gamma in that case. There is something concept. If you have learned physics in earlier standards, then if you know the sound waves and isothermal elastic properties of air, there we use this gamma and some diversion from the topic I will discuss. If you have later on, we will discuss that. So longitudinal stress and longitudinal strain. So that is longitudinal means lengthwise. So whatever the stress you apply, if it causes change in length, then we call longitudinal stress. Basically ये longitudinal stress की दो type में होता है हमारा. एक minute, हाँ. Why this PPT is Okay. Yeah. So longitudinal stress. So longitudinal stress can be either tensile or it can be compressive. ठीक है, वो एक तो कंप्रेसिव हो सकता है या फिर टेंसाइल हो सकता है. ठीक है, फॉर एग्जांपल अगर मैं एक टेंसाइल केस लेता हूँ, टेंसाइल और कंप्रेसिव में डिफरेंस क्या है तो मैं ऑलरेडी मैंने बताया कि डिफरेंस इतना ही है कि जस्ट हमारा क्या होगा, इलोंगेशन होगा या फिर कंप्रेशन होगा. सो प्लस माइनस साइन का डिफरेंस है. लेट्स से आई हैव अ सिंपल वायर और a rod which I am pulling it by applying load P. ये load P मैंने apply किया. The original length of the wire was let's say L, and after the elongation I get the elongation like this. Okay, and the new length I am assuming as let's say L plus delta L. Okay, so what is my normal stress here or the tensile stress? The tensile stress sigma here, it will be what? क्या होगा मेरा tensile stress? So tensile stress will be load upon the cross section area. Let us assume that the area of cross section is A. Okay, that is area of cross section. Okay, so load upon area, and what is the elongation? I am getting it is delta L upon L. Right, now what is my Young's modulus? Young's modulus I can define E. What is E? It is sigma upon small e. What is sigma? It is load upon area. And what is the elongation? It is delta L upon original length. तो इसको अगर मैं सिंप्लीफाई करता हूँ तो व्हाट आई विल गेट, क्या मिलेगा मुझे अगर मैं इसको ऊपर भेज देता हूँ तो इट विल बी इक्वल टू पी एल अपॉन डेल्टा एल इंटू एरिया. ओके, अगर इसको रीअरेंज किया तो आई कैन कैलकुलेट द इलोंगेशन एल एज पी एल बाय ए ई. Now this is the formula which we'll be using frequently to calculate the elongation if it is subjected to tensile stress, or it can be used for compressive also. Only delta L will be negative. Getting it? So whatever the star marking I am doing, these are for you to remember when we'll solve the numerical problems. So this is nothing but my Young's modulus. Okay. Now this Young's modulus is only applicable to what? The Young's modulus is only applicable to solids. Solids as well as liquids. It can be, मतलब जिसमें elongation हो सकता है उनके लिए हम लोग solid में, majorly for all the metals the Young's modulus can be calculated. Now the second one is the another type of modulus which we know as the bulk modulus. It is known as bulk modulus. Okay, it is denoted by small k. It is also known as called as volume stress. Volume stress upon the volume strain. Okay, now what is volume stress upon volume strain? For example, अभी ये जो हमने यंग्स मॉडुलस देखा, यंग्स मॉडुलस एंड बल्क मॉडुलस में इतना ही डिफरेंस है कि यंग्स मॉडुलस में जो मटेरियल पे हम लोग लोड एक्ट करते हैं वो भी परपेंडिकुलर है. बल्क मॉडुलस में भी जो मटेरियल लोड पे लोड एक्ट करेगा या फोर्स एक्ट करेगा वो भी परपेंडिकुलर रहेगा एरिया को. बट द डिफरेंस इज इन यंग्स मॉडुलस और इन यंग्स मॉडुलस you will have the load acting on any cross section or any particular section of the body, whereas in bulk modulus on the entire surface area the load is acting. For example, the very most common example is, let's say I have a sphere. ठीक है, which is submerged in water. तो water में submerge करेगा तो water का pressure act करेगा ये sphere पे. Pressure मतलब it will act on hydrostatic pressure, we call it as. सब side से pressure act करेगा इसके ऊपर, right? मतलब force act. Pressure is nothing but a force. Here why we are calling it as stress के बदले pressure, because I just now at the start of the lecture I explained you pressure acts on entire surface rather than stress acts on only particular area of the object. तो यहाँ पे ये जो load है वो सब जगह से act कर रहा है on entire surface area, where A here, A is the area of surface, or we also call it as surface area. ठीक है, this A can be called as surface area. Okay, this A will be called as surface area. Now what will happen, because of this the volume is going to decrease. इसका volume क्या हो जाएगा, थोड़ा सा कम हो जाएगा. So if the original volume was V, now the volume can be V minus dV. So there is a change in volume. So V is the original volume, right? And delta V is change in volume. Now in this case we are assuming delta V as negative because volume decrease हो रहा है. And let's say the pressure or the change in pressure is acting as delta P. So I am calling it as delta P is nothing but the change in pressure और बेसिकली इस प्रेशर को ही हम लोग क्या बोलते हैं? प्रेशर इज नथिंग बट द वॉल्यूम स्ट्रेस. It is the volume stress which is acting on entire surface area. Okay, so therefore what is my bulk modulus in this case now? So my bulk modulus K can be defined as what? It can be delta, sorry, not delta, it is the volume stress. The volume stress I have denoted by delta P upon the volume strain, which is delta V by V. Now this delta V I am writing negative. Here the negative sign is for decrease, indicates decrease in volume. Okay, so if you simplify this, it will be delta P into V upon delta V. Okay, so this formula will give me what? The bulk modulus. Okay, this formula will give me the bulk modulus of the material. Now this bulk modulus is valid for any of the material, that whether it is solid, liquid, gas, bulk modulus will always be there, because all the materials they have certain volume and bulk modulus always be there. This reciprocal of bulk modulus, this 1 upon K, is known as compressibility. So you should know this. Many of the times in numerical problems, they will give you compressibility instead of bulk modulus. You should know the 1 upon reciprocal, the 1 upon bulk modulus is also known as compressibility. Sorry, straight line draw karna difficult hai. Yeah, so now let's go to the next part, which is okay, C part, which is shear modulus or rigidity modulus, or we also call it as modulus of rigidity. Okay, the modulus of rigidity, it is denoted by letter G, capital G. Okay, or you also call it as shear modulus.
Hello, sir.
No, modulus of G, I am not asking him. Okay, fine.
सर नहीं सर, वो कंप्रेसिबिलिटी का साइन पूछ रहा था मैं, मतलब 1/k है तो.
Okay. 1 by compressibility का कोई notation नहीं है. You can use that compressibility as C or any other letter. There is no standard notation we use in strength of materials.
Okay, sir. Okay.
So shear modulus G. Now shear modulus, you know that कि हमने deformation देखा था. We have discussed that कि अगर मेरे पास कोई ऐसा linear object है, and if you have fixed it at one end, ठीक है, and if you apply the load on the upper end, if the load is tangential, it elongates and it gives me the lateral displacement, right? ये सब हमने पहले भी देखा था. So this lateral displacement was x and the perpendicular distance was l. So my strain here is theta, which was equal to x by l, and here the stress, the shear stress tau, was equal to load upon the area. Here A is the surface area or upper surface area. It was the only upper surface area. Okay. Okay. So what is my G then? Then G will be equal to tau divided by theta, or it can be tau is nothing but load upon area and theta is nothing but x upon L. So you can define this as PL upon x into A. Okay, so that is equal to your G, that is rigidity modulus. Okay, this is also you can remember. So these are the three different modulus we can define for any of the material. Most of the metals, they have all three modulus. Most if I take air, water, they have bulk modulus because they have certain volume, they don't have a particular shape. So rigidity modulus सबके लिए compulsory नहीं होता. Rigidity modulus is only for those who have certain shape. Okay. Now let's go to the next particular point. I guess how much is the time? We have still 10-15 minutes. So let's quickly discuss the another point known as Poisson's ratio. Okay. So again, Poisson's ratio. Now we know that whenever is material is subjected to one type of stress, yeah, load in the one direction, it not only deforms in that particular direction, it also deforms in other dimensions also. For example, मतलब क्या कि अगर एग्जांपल मैं लेता हूँ, लेट्स से मेरे पास एक सिंपल ऐसा बड़ा सा रॉड था, ठीक है, सॉरी, लेट्स से मेरे पास एक बड़ा रॉड है, and that rod I am elongating. That rod I am elongating by applying load. मैं लोड अप्लाई कर रहा हूँ और मैं उसे इलोंगेट करने का ट्राई करता हूँ, ठीक है, दैट रॉड आई एम इलोंगेटिंग। नाउ ये लोड अप्लाई करने की वजह से क्या हुआ, तो लोड अप्लाई करने की वजह से इसका इलोंगेशन हुआ, बट इलोंगेशन के बाद यू विल ऑब्जर्व दैट कि उसका क्रॉस सेक्शन भी कम हो चुका है। You will observe that it has increased in the length, but it has shown the reduction in the cross section, ठीक है, this is most common. So यहाँ पे original length L था, the new length was L plus delta L. The original diameter जो था वो D था, the new diameter is D minus delta D, ठीक है. So there are two dimensions which are changing simultaneously, ठीक है. तो यहाँ पे जो लोड के अक्रॉस हो रहा है elongation, तो यहाँ पे दो स्ट्रेन्स आएंगे. As we know the strain is change in dimension upon original dimension. As we have two dimensions which are changing here, we'll have two types of strains. One is the longitudinal strain. One is the longitudinal strain. Okay, and that longitudinal strain is nothing but change in length upon original length. Okay, and the other one is the lateral strain. Other one is known as lateral strain, that is change in diameter. अब यहाँ पे diameter decrease हो रहा है इसलिए मैंने माइनस साइन लिखा. Of course होगा कि एक अगर बढ़ता है तो दूसरा स्ट्रेन कम होने वाला है, तो दोनों में से किसी एक के पास नेगेटिव साइन होगा, ठीक है. So lateral strain is delta D by D. Okay, now the ratio of these two is known as Poisson's ratio, and that is denoted by letter mu, or it is also known as 1 by m. Okay, now what is this mu? So this mu is nothing but the modular, it is nothing but the Poisson's ratio. So what is Poisson's ratio? So mu is nothing but it is the lateral strain upon the longitudinal strain. It is lateral strain upon longitudinal strain. So lateral strain क्या है? Delta L upon L, and longitudinal strain क्या है? Minus delta D upon D. So therefore it can be negative also. ठीक है. Now ये mu को मैंने लिखा है 1 by m. See here, mu को मैंने क्या लिखा है? 1 by m. This mu can also be written as 1 by m. अगर 1 by m हो गया तो ये क्या हो जाएगा? Longitudinal strain upon lateral strain हो जाएगा. Sorry, I made a mistake. अगर मैं ये m लिखता हूँ यहाँ पे, तो ये m हो जाएगा 1 by mu, which is longitudinal strain upon lateral strain. Okay, lateral strain. So then this m stands, it is also called as modular ratio. Okay, so either the Poisson's ratio will be given or a modular ratio is given, but these ratios, they don't have any unit, they have certain values. If you take our mu ka value, तो the actual value of mu is lies between -1 to 0.5, but practically जब हम लोग use करते हैं उसका negative sign, we know that it is only for the reduction or the decrease show करता है. Negative sign का वैसे mathematically significance नहीं है यहाँ पे. Therefore in real practice when we use engineering problems, so we use mu ka value between 0 to 0.5. All the materials, they show mu value between 0 to 0.5. You can see the ranges I have given. If you have a glass material, it lies between very less mu, that is 0.05 to 0.1, very less change in the lateral dimension. Sorry. But if you have 0.1 to 0.2 for concrete materials, the reinforced concrete materials which we use, then 0.25 to 0.42 for most of the engineering materials, starting from all the good conductors, bad conductors, जो भी materials हम लोग mostly use करते हैं, all of them they range lie between this particular range. Steel having the steel जो हम लोग most commonly use करते हैं has the 0.3 as the modulus, Poisson's ratio, and 1 by 3 as the 3 as the modular ratio, and 0.33 as the Poisson's ratio. Okay. Then
hello sir.
Yes.
So actually in the formula of mu, it is lateral strain upon longitudinal strain, right? So right let me
मैंने right में लिखते हुए किया. You can, मैं कभी कभी बोलते वक्त गलत बोल सकता हूँ. You can rightly point me. Very good. Yes, I am very happy that you all are active. Who was this to notice?
Om sir.
अच्छा ओम है क्या? Okay. ओम तो एक्टिव होता ही है, बाकी क्या क्या है? Nobody else. Okay. तुमने अगर notify किया, let me know. I don't mind it. Might be हो सकता है सर. Okay, fine. Good, very good. So I expect from others as well to notify my mistakes. Or next lecture, I'll purposely make some mistakes. and let's see how many of you can notify. Okay, 0.5 for pure rubber and perfectly plastic materials. These rubbers they tend to elongate very high. मतलब रबर को अगर तुमने देखा रहेगा, तुमने उसको elongate किया, तो उसका ये जो lateral dimension है, cross section drastically कम होता है, इसलिए 0.5 ज़्यादा है. मतलब म्यू का वैल्यू उसके लिए comparatively ज़्यादा होता है as compared to materials. Okay, so I hope you know this. What is Poisson's ratio and what is the different ranges and what is modular ratio. Okay, now let's go to the next one, the relationship. Now this also it was earlier mentioned. As you know, for metals they have all three type of modulus. So there is a relation between Young's modulus, bulk modulus, and the rigidity modulus. So this relation we should know. Of course, there is a
Excuse
derivation
me, sir.
based on this. Yes.
सर आप लास्ट स्लाइड अभी जो आपने दिखाया तो वापस दिखा सकते हो स्क्रीन पर?
Yes, this one. Okay,
Yes.
I'll be sharing the slides with you afterwards. So उसके ऊपर सब कुछ रहेगा. You can don't worry. You can notify or you can write down. You can start creating your notes on your own with the help of these slides. Okay.
Okay, sir. Thank you.
Yeah. Thank you. So next, relationship between elastic constants and the this one. So as you know, E is the modulus of elasticity. So it has relation between E and K. You can see this relation. Okay. So all these are relations just to have the if you know one or two values, if you know the value of E and value of K, you can calculate mu, or if you know the mu for material and if you know E for the material, you can calculate other values. Okay, so for that purpose, all these are required, and this slide is very important because whenever we come to numericals, we are required to know this. So this slide is itself star mark. We should remember this. Okay. Of course, there is a derivation based for all these formulas to derive. I'm not going into derivation right now because mostly not required. But still, those who want, they can come to me personally, or they can give me the request on WhatsApp or Google Classroom where I can upload the derivation for this, and they can go through it. If they don't understand, I will come back to that. Okay. Yeah, do remember this. Now let's go to the next one. That is a basic numerical, but I guess we are running short of time, so I will solve these numericals and I will continue this in the afternoon class. Now basically the afternoon class, I stopped sharing it. Basically